All right. This one here is if you have a large sample. Uh, Large kind of, when they're talking about that, they're talking about right around 30 or more, kind of from the central limit theorem is where they're coming up with that. Today's is a lot of vocabulary for chapter 6, at least at the front end here. And then towards the end, hopefully it will make sense as to why they have what are called confidence intervals and a margin of error. I think you've all heard of a margin of error for any polling. They're like, oh, the percentage of approval normally of the president is 40-some% with a margin of error of 2%, which means it could be too higher or too lower, right? But they're not 100% sure of that. They're only about 95% sure of that, okay? So they're only 95% confident that that's where it is, okay? We're going to talk about that today. A point estimate, you are very familiar with point estimates. We've been doing them all year. It's a single value estimate for some parameter. And the ones that we've been doing is the mean. Instead of mu, we have x bar. And that's the most unbiased point estimate that you can have. In this case, meaning not affected by other thing, unbiased. And for this first example, we're going to use the calculator to do some of this work for us. Because I think you're getting pretty good at understanding, what standard deviation means, what mean means, what x bar is. And so as we're kind of reading through this one, go get a graphing calculator if you don't have one. So I have 250 students that are enrolled in my 4th period underwater basket weaving class. It's a big pool. I am lazy, and I don't want to calculate the actual average for all of my students, because they just took a test, And so he takes the 30 percentages listed below to calculate a sample mean. That would be the sample average, right? Because it's not all 250 students. And so what do I get for the sample mean? And we're also going to make a note of the sample standard deviation when we get in there. Okay? So do you have your calculators ready? All right, so does anybody, we haven't done this in a while, so does anybody remember, obviously we could add these all up, right, to find the mean, add them all up and divide by 30. That'd be easy, right? But that wouldn't give us a standard deviation, right? We'd have to do all that work, and oh my goodness, it would be terrible. And so we don't want to do that. We could use Excel, of course, but the TI-83 is a pretty good way of doing it as well. So how do we go in there and actually kind of give it these numbers? There's lots of ways you can do it, but there's one way that at least keeps the numbers for you. Yes? Go to hit stat, okay, so hit stat, okay. Yeah, we want to edit something, and when you're editing something in stat, you're editing a list of numbers. Okay, so let's go ahead and edit that. Oh my goodness, I have a ton of numbers in there. Do we know how many numbers in there? I don't know, there could be a lot, right? Do most of you have a lot of numbers in there? Oh, well, I have a lot, so here's what I'm going to do first, because I don't want to sit here and make a mistake. So what I'm going to do is I'm going to go back to stat. Okay, you can stop. Okay, that was weird. All right, so you go here, and what do you suppose I'm going to do? I want to get all those numbers out of there. Yeah, clear list. And so I'm going to hit number 4, and then right above my number 1 here is a little L1. You see that? So I'm going to hit the blue, and then I'm going to hit the 1, and so then I'm going to clear that first list, because I don't want all that stuff in there. If you don't have anything in there, you don't have to clear it. Okay? But I do have a lot of stuff, and I don't really want it there. Oh, it's done. Okay. So now let's go back in there where we were told to go, and we are going to edit that list. Ah, look, they're all gone. And so then you just start typing your numbers. 78, enter. 72, enter. And you just keep on going. And you keep doing it, I'll keep doing it, and hopefully we get the same number in the end. That'd be great. I was going to have these all entered, but then I decided not to. Because at least now you get to see me entering all these numbers. It's lots of fun. And you can see by these scores, this is a very difficult class. It's a joke. Whoops. Now I don't know which one I was on. after 87, huh? 83. Okay. And 94. Oh, I'm almost there. So see, this is why I'm lazy, because I didn't want to do this for all 250 kids. I hope that's right. And seeing this one down here is L31, I feel good that I've at least entered 30 numbers, right? Because I'm on a blank, right? So I feel pretty good. Oh, I'm up there. Oh, that's L30. I feel fairly confident that I've at least entered 30 numbers, right? So that's a good start. Okay, that still has... So whoever suggested that was a horrible idea, because that doesn't tell me the mean. It just tells me that that cell is 76. Well, now what? Yes. Oh, hit stat again? Okay. Oh, so go over to calculate. Okay. Yeah, one variable statistics. It'll tell you everything that you need to know. Yep. And, okay, that didn't do anything. Nope. You got to put L1 up there. Yep, because that's where you put all your information. So alpha 1. One variable stats of L1. It may default to L1. I don't know if it does or not. It's right above the 1 here. There's an L1. You just have to alpha, or the second and 1. Is yours alpha? Is that what yours is? Or?
I don't know. No.
All right, we have all this lovely stuff here. X bar is 77. It's as if I made it happen nicely. I don't know. That's weird. So X bar is 77. Now, how come they don't call it mu? Well, it could be a mean of a population, but they don't know, so they're safe, and they just say X bar, right? And plus, maybe they just don't have mu on here, and they don't want to mess with that. Okay. So 77 is our mean. And now, which of these down here? We seem to have two standard deviations. We have this big S in front of the X, which is 12.575, blah, blah, blah. And then sigma X, which is 12.36. Which one is the one that we're going to be looking at? They're both standard deviation. One is of a sample, and one is of the population. Yeah, we want the sample. Which one's the sample?
Small.
Yeah, with the big S is sample. Remember, sigma, the actual Greek letter sigma, is population. But I didn't enter the population, so how could they possibly know? No, they just divided by n instead of n minus 1. That's all they did. And so this one, really, to be honest with you, this only works if you know you had the population. Then that's actually right. But do we have the population here? No. Again, I only entered 30 of the 250. How could they possibly know the standard deviation of all 250? They can't. It's impossible. But they can do this. Of my sample, they can figure out that we're at about 12.58, right? And my mean is 77. Well, that was all fun and good, so let's write that down. And where is it? Here it is. And get that out of here. And there we go. X bar is 77. S for standard deviation, that is, remember when you use S, that means of a sample. When you use that little sigma, it means otherwise. It is 12.58. Now here's the important question. And the question that leads to this entire chapter. Do you think 77 is the population average? Could it be? I mean, exactly 77. Do you think that's it? Yeah, relatively close probably, right? If I took a good sample of it. But maybe I just took the first 30 for all we know. Maybe it went A through B or something. A through D. Said, here's the scores. So we don't know, but chances are, if you're taking 30, it's probably relatively good. Now, what if I said, on the other hand, I said, I believe the mean is somewhere between 75 and 79. Do you believe that's getting a little bit more accurate?
Yes.
Okay. And that's the whole idea of confidence intervals. You're going to get some sample number. Is it a chance that that's actually the number for the population? There's a chance, but is it a big chance? No. And so what we do is we open things up. We say, well, what about from here to here? And then you say, well, I'm 90% confident that's right. I'm 95% or 99%. Those are your three big ones. Or you can say, I'm only 50% sure. No, that's not very good, is it? All right. And so we're going to start opening this up to intervals to hopefully actually get the real answer in there somewhere. And let's face it, for 250 people, could I actually go find the real answer? I could, but I don't want to. But now think about when they poll for presidencies. Are they actually ever going to get that population? No, so they take samples. And that's why they always say, oh, it's this number within 2%. or within 3%, or something like that. And we're going to look at, in this chapter, how do they come up with that? Like, they just make that up, or is there actually numbers for that? So instead of doing remember this is a point estimate, we're going to do an interval estimate, kind of like the, what did I say, 75 to 79, you know, that's giving you a much better range. And that's really what that is. It's just a range of values used to estimate that parameter. Instead of just one point, we're going to just use a bigger range. Now, are we going to base our range off of something we found? Yeah, I'm not just going to look at those numbers and say, oh, I think the average is 70. So I think it's 68 to 72. Yeah, you're going to base it off of something. And you're going to base it off of that sample mean that you have. Your level of confidence. So how confident are you? Here's the big three right down there, 90, 95, and 99% confident. Okay. Obviously, you could go any confidence interval you wanted to because you have that little Z table that you could figure out what percentage you need. But level of confidence will be notated with a C like that, a little italicized lowercase c kind of thing. This one's kind of long, so I would definitely suggest, well, I guess it's not that long, but paraphrasing it, the probability that that interval estimate that you just gave me actually contains the right answer, meaning the population parameter, normally the mean, right? So it's the probability. So maybe 95% of the time, it'll actually have the right answer in there. But that means 5% of the time, it doesn't. But that's pretty good, right? I mean, and 90% and 99% obviously is very sure that you're actually getting the right answer in there somewhere. So obviously the more confident you want to be, what are you going to do with your range? Well, wider it is. Okay. Okay, if you only want to be 50% confident, you say, oh, it's in between here and here somewhere. You know, just get something very small. And here are the actual z-scores they would like you to use. 95%, you might think you know that one, but it is somewhat rounded. You might want to say 2, but not quite. You could look these up in your table. In fact, that one we've used a lot for 90%, haven't we? The 1.645, haven't we? Kind of come to that one a lot. And the actual number there is 1.96, which is very close to 2. And then 99%, the z-score is 2.575. Again, you could look that up in your little table. But I don't think 0.95 ever exactly happened, right? It was always kind of in between some stuff. 0.90 never exactly happened in that table. And so they're telling you this is what we'll use for that z-score. So these would be 3 I would suggest maybe you kind of, I don't like to use the word memorize, but know them well, okay? Because these are the main 3. And if you need some of the other ones, be able to go get them from the table. And that table will be good enough, okay? Whatever you estimate it to be. All right, so far, you getting the idea? We're going to find some point, but we're going to widen that out so that we're really sure we have the right answer in there somewhere, okay? Margin of error. I've already talked about that a couple times today. What do you suppose that margin of error is? Normally notated with an E. Like in the examples I've been given, yeah. No, not quite. Yeah. He said it was the probability that it's not right. That's not the margin for error. No, that's kind of what he was saying. It's the opposite of the 90%. Margin of error is kind of like the, what did I add? 2 left and right of that number we had earlier. So yeah, it's how much you add and subtract. That's your margin of error. You're saying, it could be 2 to the right, it could be 2 to the left. Or maybe it's 5 to the right and 5 to the left, who knows? But margin of error is how much you're adding and subtracting to it to actually get that confident. Okay, and you're actually going to find out exactly how much you have to add and subtract to be a certain amount confident. They work hand in hand. Okay? So this one I think is the long one. Yeah. That's just because it has a lot of other names. It's the greatest possible distance between the point estimate. For us, that was what, 77 in our first example? And the value of the parameter it is estimated giving a level of confidence. So for us, I said, oh, let's add 2, 75, or subtract 2, 75 to 79, right? Did I ever tell you how confident that would make me? No, because I don't know. I'd have to do the calculation. But my margin of error there, I said, was going to be 2, okay? Plus or minus 2%. And that's what that was. And this could be known as the maximum error or the estimate of error tolerance. And yeah, so yeah. Or excuse me, the maximum error of estimate or the error tolerance. I'm going to refer to it as the margin of error because that's how I know it. Again, it's how much you have to add and subtract to be sure. And we're almost done with definitions here, and we're going to get into some more actual applications of these words. And I have one slide up here that is not on your notes, but you may want to add something similar on your notes somewhere. It was just going to be too big to fit on there. I can always print it off for you if you would like it. But all right, here's your margin of error. I think you have that down at the bottom, right? Or no, next page. All right. And I think I left some of the writing in there. No, I did not. So error is some z-score based on whatever confidence interval you want. So that means you're going to use one of those z-scores you had on the other side, right? If you want 90% confident, you're going to use 1.645 for that z-score. If you want 95%, you're going to use 1.96. If you want 99%, you're going to use 2.575. That's what number is going to go in there. It's basically whichever z-score gets you to the level of confidence you want. And again, you could find those on that little normal distribution table. And we've seen this. Where have we seen that? Last chapter. And what is that? That's the standard deviation of the sample mean. Okay. Well, good thing we wrote that down earlier, huh? It's like I was planning ahead or something. And all they did is they rewrote it over here. Remember, that's what we did last chapter to actually get that. We took the standard deviation of the whole thing and divided by the square root of it. And here's what it says. This one's important. Highlight that. It's like a little asterisk. Once again, do you think when they do those presidential polls, they actually know the standard deviation of the entire population? No way. They don't even know the mean of the entire population. How are they going to know the standard deviation if you don't know the mean? Right? Because you base it off the mean? There's no way. And so what they say, as long as you're big enough, which is n greater than or equal to 30, which is what we did, right? We had 30 in our sample that I gave you, right? The sample standard deviation, S, can be used in place of the population. They're saying if you've gone at least 30, it's good enough. Right? So we can replace that S. And in our problem, S was what, 12.58 or something like that? Or yeah, 12.5758, something like that. So we're going to be able to use that. That's the hard thing about stats, because normally you don't actually know the entire mean and you don't know the standard deviation either. So you have to infer. You have to use the information you have. Okay? Is there anything down here? Oh, yeah, just the stuff I pulled down. Okay. Well, let's work with this thing here. Use the information from example 1 and subsequent notes to determine the margin of error at a 95% confidence interval for example 1. All right. For example 1, so our error, E, equals. So if we want 95% confidence interval, what is my z-score? .96, do we agree with that? Okay, so that's z sub c is what that is. That's my z-score based on my confidence interval. Okay? Now realize any number can really go there. Okay? Then it says times, do I know sigma for the population here? I do not. I don't know all 250, do I? I don't know the standard deviation for that. But I do know the standard deviation for my sample, which was 30 or more. So I can just use the S, which we wrote down as 12.58, correct? So that's basically our S, because our sample was big enough. But wait a minute. This is we're dealing with this, right? So we have to divide by square root of n, because that's how we find our standard deviation, right? What's n? 30, right? There is a scrunched eyebrow. Well, if you actually know the standard deviation of the entire population, use it. If you don't, and your sample's 30 or bigger, you can just use the sample standard deviation.
Is there something 30 or bigger?
Right. That's why we're able to use S. Because we actually don't know for the population. We have no idea. And we really have no idea because I didn't actually come up with all those test scores. I just made them up. There could be somebody that cheated and got a 0 out there for all we know. I don't know how you would cheat on underwater basket weaving, but they did. All right? And so they got a 0. Maybe they did it on land and then you fail. All right? And so we normally will not know the standard deviation of the entire population. So they're saying as long as your sample size is 30 or more, go ahead and just use your sample standard deviation, which the calculator was nice enough to give us, which is also why we went to the calculator for that first example. It probably would have been quicker just to add 30, add them all up and divide by 30, but then we wouldn't have had the sample standard deviation. All right, so this right here is going to tell us what? So go ahead and do that calculation. Yeah, watch your parentheses if you try and type the whole thing in. Or just do the stuff in parentheses and take it times 1.96 is another way to do that. It technically is plus or minus here, yep, but normally when we talk about error, we don't say plus or minus. It's understood by all the statisticians that you add and subtract that amount. But if you want to write plus or minus, I'm not going to make it wrong. Okay? And it is actually going to come out as a percent, I believe. You don't have to move decimals or anything. It knows you're talking about a percent here. Yes? Yeah, let's just say 4.5, right? Well, we better do approximately, right? Now, really, what does that mean for this example? Yeah, now, if you can put this all together, you've got this confidence interval thing kind of figured out, if you can put this all together, yeah. Okay, yeah. So basically, we thought the mean was what? 77. But that's really x bar, right? So mu, which is the actual mean, we are 95% confident that mu is between, if I take 77 and add 4.5 and subtract 4.5, I know it's between those two numbers. And what those numbers happen to be, in a way, it's like standard deviation, but what you're doing, because that's really what you're doing, you're getting it out far enough so that it works. You're saying, because here's your standard deviation right here of your sample. That's this big stuff in parentheses. And then you're saying, well, how far out would I like you to go? Well, about 2, because I want to be 95% confident. And then that's kind of what you're doing, exactly. Because really, remember, this came from central limit theorem, this big stuff in parentheses, right? Okay. And now we're just saying how far out I'd like it to go. 2, which gives me 95% confident, because that's what relates to 2 as a z-score, or 1.96. So here, we're saying the actual mean, that's what mu is in there for, right? Is going to be between 72.5 and 81.5. Did I just make those up? Did those just come out of nowhere? No, I took what I got for x bar, which was 77, right? And I added 4.5, and I subtracted 4.5, right? So but I'm not 100% sure. In this case, we are 95% sure. So what do you suppose is going to happen if I turn around and go for 99% sure? This 1.96 is going to get bigger, right? And so is the 4.5 going to get bigger or smaller? Bigger, probably by quite a bit, right? Because what is it, 2 point, if you change it, it's 2 point, I lost my notes. Well, wherever my notes. Yeah, 2.575. So that's going to get a lot bigger. But if I only went for 90%, that range is going to get smaller. Yes? They could, but when they poll, they do about 1,000. And we're going to talk about why they do 1,000 in a little while, because of how they want to get really, really close. And that's why normally those polls are within 3%, 2%. I saw one that was just 1%. Okay, so, but to get to like 1% and be 99% confident, that's a lot of people you got to poll. Okay, so they go down a little bit because it's what's called diminishing returns. They can keep polling more people, but it really doesn't get as better as you think. It's kind of like a batting average. You would think if you just really did well, it would just go up really fast. But it really doesn't work that way. It kind of slows down, any of you that have been in baseball, or even free throw percentage. It doesn't go up as fast as you think it was after a long time, right? After 1,000 free throws, it takes a long time for you to move that free throw percentage up, right? It's the same idea. And so they say after about 1,000, they're really not getting a whole lot more accurate by doing more people. And they're like, forget it then. We're just going to do about 1,000 and be done with it. Okay? So what I will show you now is how can we use that TI-83 to kind of check that interval that we obtained in example 2. All right? So let's just see how good we are here. And we don't need that. Clear? So go to stat again. But this time we're going to go to tests. We're going to test our idea here. And we're going to test our what? Our interval. Oh, look at that. It's amazing as if they know what we want. So number 7 down there. We want Z interval is the one you want to hit. And we will input some data for them. So we can just hit enter for that one. All right. Do we know basically sigma to the best of our abilities? We do, right? What is it? To the best of our ability, we know that it is? Nope. 12.58. Right? That's to the best of our ability. And where would they like to get the information from? Did we put all the information in list 1? Yes. Frequency, I only want to use them once. Right? I don't want to use them bunches of times. What's my C? What did we say here? We wanted 95%. Is that about what we got? I went down to calculate and hit enter. Is that pretty close to what we came up with? Yeah, they rounded a little bit, right? But 72.5 to 81.5? Yeah, so I think we're believable here, right? Now, I believe I know what the next slide is. Let's find out if I do or not. And I don't. I was wrong. Here's the whole idea. This is the one that's not on your, this is to help you out. This picture, again, is talking about confidence intervals. Did you notice we never said 100%? Right? 90, 95, 99. So let's say mu is actually here. When you do these, do you actually know what the answer is normally? No, you don't. That's the hard part, right? But what you do is you try and put a bunch of ranges out there, and that's what all these horizontal lines are. This is somebody's range out there that they found. So for example, this person right up here found that that was, I don't like this new feature, but anyway, they found that's their mean, and so they went left and right the amount they were supposed to, but did they actually have the correct answer in their range on the one that I put the dot on? No. How about this one here? Maybe that's their average that they found, right? And then they went left and right the amount they were supposed to. Did that one actually have the correct answer in it? Yep. Yeah. And then this person down here, the mean on that one's probably right about in the middle, right? That person actually got really close. But did they really know they got really close? That's the problem. Not really. They went left and right, the margin of error they were supposed to. Now some people think all of these should be lying, right? It have the mean in there somewhere. How come they don't all have the mean in there? Yeah, I'm only so sure. So if I was 90% confident, I would predict that 9 out of 10 of these would actually have the answer in it. If I'm 95%, then 95 out of 100 should have the right answer in there. Okay? So this one, yeah, I'm only how percent sure on this one? I think there's 10, isn't there? So 12. So I'm 10 out of 12% sure in this one. Okay? Now you're probably saying, well, how do they know this? If they don't know the answers to these, how did they know this is working out right? Well, they took ones they did know the answer to, and they ran all these samples and found out how close they'd get. And that's what they found out. They found out if you do it this way, that's how close you get. Okay. Do you understand the picture and what I'm trying to tell you of why that if you take that margin of error, it should at least try and go over and hit the right answer? Did this one up here quite make it? Nope, not quite, right? It tried. It tried to get over there, but it wasn't quite good enough. This one also tried. Didn't make it. All the rest of these actually have the correct answer in there, in the range that they were given. Okay? Does that make sense? Okay? Because there's a lot of college students that don't get that. So that's the best way I could figure out to show you a picture. So all of those are somebody's, like each one of you did a sample and each one of you is up there somewhere. Some of you hit it, some of you didn't. The hard part is you don't really know if you did or not. Okay? So what I would like you to do right now is to try this one on your own without any guidance from me. I believe I've given you enough here. So Director of Admissions, they want to estimate the mean age of all students currently enrolled. A random sample of 20 students was given. The mean age is found to be 22.9. From past studies, now wait a minute, do you notice something? Something should be just bells ringing here real quick. when you read one of those numbers? 20. That's a problem, right? Because to use S, which is the sample standard deviation, you need at least 30. But then you keep reading, it says, from the past studies, the standard deviation is known to be 1.5. So do we actually know sigma? Yeah, we do. So do we need S then? No, because we got sigma, we're good, okay? To be 1.5 years. Construct a 90% confidence interval of the population mean age. Okay? So try and use all the stuff that we've talked about today to give me an interval that would make me 90% confident that I actually got the right answer in there. And I'll pause it while you do that. Well, looks like a lot of you got right to that one. We'll see how you did. So we know the mean, right? We don't have to sit there and calculate that. What would the mean be called there? That 22.9, that's a what based on the notes for today? X bar or a point estimate, right? And what we're looking for is an interval estimate, right? And it's a confidence interval. And so what we have to do is we got to say, well, what's our error? So our error, we got to find some z-score, correct? And what z-score is going to correlate to 90% confidence? 1.645. Very good. So there's your z-score. Now, here we either need S or sigma here, and we actually have sigma this time of 1.5. Very luckily, because, again, 20 wasn't going to be enough. Okay? And then what you do is divide by square root of 20. Okay. And it is 0.55. Because in the formula, you divide by square root of n whether you know actual sigma or S. Okay, the sample. You have to divide anyways. Because of the central limit theorem. And what is that 0.55? Is that my answer then? Students are a half year old? Is that what it is? That's my margin of error. And so we know that mu then, well, better not put, yeah, we won't put equal to on there. Well, 22.9 is kind of my X bar, right? So how does the 0.55 relate to the 22.9? Well, and it's subtracted, right? And so it has to be less than, so it'll be this number I'm looking for. 23 point, is it 45? Yep. And down here, 22.35. So they're saying mu is somewhere between 22.35 and 23.45. Are they saying that it's 22.9? No, that's not what this is saying. It could be, but it could also be 22.3. It could be, right? Because we're only how confident? 90%. And if the actual mean was 22.3, did this hit it? No, it didn't, did it? Didn't quite make it. Got close, didn't quite make it. But we know 90% of the time, if you do this, you're going to hit the actual answer in there somewhere. Okay? So that go okay for everybody? That's right. Now what if I switch the question around like I did right here? So how many tests should I take? I only took how many? 30 before? And I got to 95% confident, right? So how many should I take in order to be 99% confident that the sample mean is within 3% of the actual mean? So I flipped the question around on you a little bit, right? So let's see, what can we fill in? Well, I better not do that, right? I better just give you the full formula here. Well, what am I looking for? Of all the, look at that formula. It's just letters everywhere. Of that, what am I looking for? What don't I know? N is what I don't know. And look how trapped that thing is. It's way in there because I want to know the number of tests, the number, how big my sample should have been to actually get within 3% and be 99% confident. Do you think it's going to be more than 30 or less? Do you think it'll be considerably more than 30? Well, we'll find out. So can anybody tell me what any of this should be? 2.5, what is it? 2.57. Now, how did you come to that number? Whoops. Is that right? 2.575? Okay. Okay, that's good. That's your z-score because of the 99%, right? Yes. E is 3. Very good. That's my error. I want to be within 3%. Anything else? Yeah. Nope, not for this one. This is back to mine. 12.58. This one's back to mine. Right? Not back to the last example. This is back to mine. And yeah, and I don't know, right? But at least everything else is filled in. So then how would one even start this process? Yeah, get the 2.575 out of there, right? Did I give you enough time to write this down? I don't mean to go fast, but we're running short on time here. We always run short on time in here. Why is that? All right. 2.575, right? Divide by that. Yeah, we're going to have to round that a little bit. Is it 1.16 or something like that? So we'll say 1.165 I have. Let's do that. Equals all of that stuff, right? Yeah, this is the one where you, once you know how to do these, it's basically the square root of n and the 1.165 are just going to trade places. And what you're going to do is basically multiply both sides by the square root of n, right? Because it'll cancel over here. Because who wants a variable in the denominator? Nobody wants it down there. And so once you get here, I better not use that column. You get 1.165 times the square root of n equals 12.58. So do you see how they're really going to end up just changing places in that setup? Right? And square root of n is going to be that decimal, correct? And square root of n is, did I write that down somewhere? 10.798 or something like that, right? And yes, you have to square it. So n is 116.6, and in this case it's 116.6 scores or tests or something like that, right? So let's face it, if I'm going to need that many tests, I might as well just do them all, right? If I'm doing 116 of them, I might as well just do all 250, because then I'd be 100% sure. So you see what I mean? You only gain 1% certainty by doing the rest of them. You see that? And I'm not even halfway. So you see why they only do a certain number of people when they test that presidential thing, because they know they're not going to get any better by doing a bunch more. Okay, so here I have to do almost more than double to gain 1% accuracy. And so what's the point? Okay? There isn't any. Okay? So any questions on confidence interval and margin of error? Because it's big and it's easy to confuse. A lot of people do.